The ideal gas law can be used to calculate the gas density. The gas density is defined as mass divided by volume, gram per liter. So let's start with ideal gas law. PV equals nRT. N is the number of moles, which can be calculated by mass divided by molar mass, m over n. Okay? So ideal gas law becomes PV equals m over molar mass times RT. In order to introduce density into this equation, we notice that there's a mass m, there's a volume here. Okay, so if we divide by volume on both sides, the left side becomes P, the right side becomes m r t divided by V, we divide by volume, and molar mass. Okay, and note that this one, mass divided by volume, is the density. So we have P equals density times RT divided by M. So to calculate the density, we both sides divide by RT over M. So when it goes to the left side, it inverses it. So pressure times molar mass divided by RT equals density, which is M over V. Okay, so we have this equation. The density is molar mass, pressure, gas constant, temperature. So the conclusion is the density of gas is directly proportional to its molar mass, m, and inversely proportional to its temperature, T. Sample problem 5.8. To apply a green chemistry approach, a chemical engineer uses waste CO2 from a manufacturing process instead of chlorofluorocarbons as a blowing agent in the production of polystyrene. Find the density in gram per liter of CO2 and the number of molecules per liter at standard temperature, pressure, and at room conditions. To calculate the density, we use the equation we derived in the last slide, and that is the molar mass times pressure divided by R divided by temperature. So standard temperature pressure means 0 degree, 1 atmosphere. 0 degree should change to Kelvin, and then plug in temperature, pressure, and the molar mass can be calculated for CO2. So we can calculate the density in gram per liter. To calculate number of molecules per liter, we first convert grams to moles, and then from moles to number of molecules. At the standard temperature, pressure, temperature is 0 degree, pressure is 1 atmosphere. So first 0 degree plus 273.15 give you Kelvin, 273 Kelvin, and pressure 1 atmosphere, and the molar mass for CO2 is 44.1 gram per mole. So plug in this equation, molar mass 44.01, pressure 1 atmosphere, temperature 273 Kelvin, and the R constant is 0.0821 atmosphere liter per mole per Kelvin. And that gives you 1.96 gram per liter. Next, we convert grams to moles, and then moles to number of molecules. So to convert to moles, we divide by molar mass. 1 mole CO2, 44.01 gram per CO2. 44.1 gram CO2. And then, so grams cancel, give you moles per liter. And then we multiply by Avogadro's number. Okay, so 1 mole is 6.022 times 10 to the 23rd power molecules. And so that gives you the number of molecules of CO2 per liter. At 20 degree, 1 atmosphere, we first convert 20 degrees to Kelvin, all right, and then plug in. So it's 298 Kelvin, molar mass, pressure, R constant, and that gives you 1.83 gram per liter. Compared to 0 degree, and this is smaller, so increase temperature, decrease density. So next, we convert first from grams to moles. So moles per liter. Okay, you divide it by molar mass, and then you multiply by Avogadro's number. So moles cancel, give you number of molecules. Using ideal gas law, we can calculate the molar mass of an ideal gas. Let's start with ideal gas law. PV equals nRT. And N is the number of moles can be calculated to be PV divided by RT. Now N is the number of moles which can also be calculated by mass divided by molar mass. So this is mass, this is molar mass. And these two should be the same. Okay? So to calculate molar mass, we can multiply by molar mass on both sides. Left side becomes M times PV divided by RT. The right side becomes M. Okay, the mass. Now, both sides divided by this term, so the left side becomes M. The right side is the mass divided by PV over RT, which equals M times RT over PV. Okay, so that's the equation we can use to calculate the molar mass if we can measure temperature, pressure, volume, and the mass of the gas phase. Sample problem 5.9 is an example how molar mass can be determined. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in a boiling water, causing the liquid to vaporize and fill the flask with gas. She closes the flask and reweigh it. She obtains the following data. Calculate the molar mass of the liquid. Now this liquid vaporized becomes a gas phase. So to calculate the molar mass of the liquid, we can calculate the molar mass of the gas phase, which we can use the equation we derived from last slide. And so to use this equation, we need to know the mass of the gas phase. And here we know the mass of the flask, the mass of the flask plus gas. The difference will be the mass. Okay, and pressure 754 torr, and temperature is Celsius, so this needs to change to Kelvin, and volume is milliliter. Okay, now the R constant we use 0.0821, but make sure the unit pressure must be atmosphere, and volume must be in liter. Okay, and then we can use gas constant 0.0821. So first change Kelvin to Celsius to Kelvin, torr to atmosphere, millimeter to liter, and then plug in everything into this equation. So first calculate the mass of the gas, which is the difference of the flask before and after vaporization. So that's the gas weight. And then the volume, milliliter, divided by 1000 give you liter. Temperature plus 273.15 give you Kelvin. Pressure, torr, divided by 760 torr, give you atmosphere. Okay, and then plug in all this data into this equation. And you should get 84.4 gram per mole. Gases mix homogeneously in any proportions. Each gas in a mixture behaves as if it were the only gas present. The pressure exerted by each gas in a mixture is called partial pressure. For example, if we have a mixture of A and B, A has a partial pressure PA, and B has a partial pressure PB. Dalton's law of partial pressure states that the total pressure in a mixture is the sum of the partial pressures of component gases. So in this mixture, the total pressure is the sum of PA and PB. The partial pressure of a gas is proportional to its mole fraction. Mole fraction is defined as the number of moles of a particular gas divided by total number of moles. So XA, the mole fraction of A, is the number of moles A, Na divided by total number of moles. And the mole fraction of B will be Nb, the number of moles of B divided by total number of moles. And obviously, XA plus XB is 1. So the mole fraction of A and B added together is 1. And the partial pressure of A is total pressure times mole fraction of A. So the more A you have, the higher the partial pressure. When XA equals 1, that means the gas only have A. According to this equation, then partial pressure of A is just the total pressure. Sample problem 510. In a study of oxygen uptake by muscle at a high altitude, a physiologist prepared an atmosphere consisting of 79 more % of nitrogen, 17 more % of oxygen 16, and 4 more % of oxygen 18. The total pressure of the mixture is 0.75 atmosphere. Calculate the mole fraction and the partial pressure of oxygen 18 in the mixture. So in the last slide, we learned that partial pressure of a gas A equals total pressure times mole fraction of A. In this case, we want to calculate oxygen 18, the partial pressure. And we know the total pressure is 0.75. Okay, so we need to know the mole fraction of oxygen 18. The question gives you mole % of oxygen. Okay, so we know mole fraction is number of moles of A divided by total number of moles. Okay, so that's the mole fraction. Now to calculate the mole %, we use the same equation but times 100. So that's how you calculate the mole %. Okay, so to calculate mole fraction, then you need to use mole % divided by 100. So that gives you this mole fraction. Okay, so first convert this mole % to a mole fraction, and then plug in this equation to calculate the partial pressure. So here we first use mole % divided by 100, give you 0.04. So instead of 4%, we have 0.04 mole fraction of oxygen 18. And then using mole fraction multiply by the total pressure, which is 0.75, give you 0.03 atmosphere. And that's the partial pressure for oxygen 18. Water has a vapor pressure that is temperature dependent. At a low temperature, vapor pressure is low. Increased temperature, increased vapor pressure. At 0 degree, vapor pressure for water is only 4.6 torr. When temperature goes to 18 Celsius, vapor pressure increases to 15.5. When temperature goes to 70 degree, vapor pressure becomes 233.7 torr. When temperature goes to 100 degree, vapor pressure of water becomes 760, which equals to the atmospheric pressure, and that's when water starts to boil. In laboratory, when we collect a certain gas, for example oxygen, it's always a mixture of oxygen with water. To find the pressure of oxygen, we need to know the partial pressure of water, and using this table, we can find the partial pressure of water if we know the temperature. This diagram shows how some gases can be produced and collected in laboratory. As an example, potassium chloride, when heated, produces oxygen gas. And oxygen gas is then bubbles through water into a collection vessel. A collection vessel is a test tube inverted, initially full of water. Okay, because oxygen has a lower density than water, so the oxygen gas goes up to the top and pushes water down. After all the gas has been collected, the height of this test tube is adjusted so that the water level inside equal to the level outside. This way, the pressure inside the test tube, which is the pressure of the gas, equal to the pressure outside, which is the atmospheric pressure. The gas inside, however, is not pure oxygen, because when the oxygen bubbles through water, water also vaporizes. So inside test tube, there's also water vapor. So it's a mixture of oxygen and water. If we know the temperature, we can find the vapor pressure of water. And using atmosphere, which is the total pressure inside, minus the vapor pressure of water at this temperature, we get the partial pressure of oxygen inside test tube. Using ideal gas law, we can calculate the amount of oxygen collected inside the test tube. Sample problem 5.11. Acetylene is produced in laboratory when calcium carbide reacts with water. So this is the acetylene. A collected sample of acetylene has a total gas pressure 738 torr and the volume of 523 milliliter. At the temperature of the gas, which is 23 degrees, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? So the total pressure, this is the total pressure, which is the sum of the partial pressures. And in the gas mixture, we have acetylene and water vapor. Okay, so this pressure should equal to the vapor pressure of water plus the pressure of acetylene. Okay, now water vapor pressure is given at 23 degrees is 21. So this is 21, and total pressure is 738. So you can calculate acetylene partial pressure. Okay, and then using ideal gas law, PV equals nRT. So this is the partial pressure of acetylene, C2H2. So that's the one we just calculated here. And the volume is given 523 milliliter. So you need to convert to liter first. Okay, and then temperature also given 23 Celsius. So first convert to Kelvin and put it into here, and we can calculate number of moles. And then from number of moles multiplied by the molar mass, we can calculate how many grams of acetylene are collected. First, we calculate the partial pressure of acetylene using total pressure minus water vapor pressure. The unit is in torr. So we can convert torr into atmosphere by dividing by 760. So that's the partial pressure of acetylene. Next, we convert the volume 523 milliliter into liter by dividing by 1000. And then temperature 23 Celsius becomes 296 Kelvin. So now we have pressure, volume, temperature using PV equals nRT. So N can be calculated by PV divided by RT. So this is pressure, volume, temperature, R is 0.0821. So that's the number of moles collected in the tube. And then multiply by the molar mass, give you grams. The answer is 0.529 grams. In Chapter 4, we learned how we can use the stoichiometry of a balanced equation to convert between the amount of reactant A and the amount of product B. In this chapter, we learned ideal gas law. So if reactants products are gases, we can now using ideal gas law to convert between the gas variables of pressure, volume, temperature of A and the pressure, volume, temperature of B. For example, if we know pressure, volume, temperature of A, we can use ideal gas law to calculate the number of moles of A, and then use the stoichiometry, we can calculate the number of moles of B. And then from number of moles B, we can calculate the pressure or volume or temperature of B. Depends on what condition we have. Sample problem 5.12. Solid lithium hydroxide is used to scrub CO2 from the air in spacecraft and submarines. It reacts with the CO2 to produce lithium carbonate and water. What volume of CO2 at 23 degrees 716 torr can be removed by reaction with 395 grams of lithium hydroxide? So first, let's write the reaction equation. The reactants are lithium hydroxide, carbon dioxide. The products are lithium carbonate and water. So here is the reaction equation. Lithium hydroxide, carbon dioxide, products, lithium carbonate, water. And to balance reaction, we add 2 here. Now the given condition is 395 grams of lithium hydroxide. So we know the grams of lithium hydroxide, and we want to calculate the volume of CO2. So we calculate the volume of CO2. Okay, so apparently we want to have conversion between the lithium hydroxide and the carbon dioxide. Okay, so according to stoichiometry, we need the moles of lithium hydroxide. So first step, we need to convert the grams to moles. That's the first step. So when we have moles of lithium hydroxide, and then we can convert to moles of CO2. That's the second step, using stoichiometry. And then the third step, when we have moles of carbon dioxide, then using ideal gas law, third step, to calculate the volume. Okay, so first step and the second step, okay, we use grams of lithium hydroxide divided by the molar mass of lithium hydroxide, which is 23.95 grams. So gram, cancel, give you moles of lithium hydroxide. And then look at the stoichiometry is 2 lithium hydroxide, 1 CO2. So using this as a conversion factor, so moles of lithium hydroxide cancel, give you moles of CO2. All right, so we have a number of moles. Now we calculate the volume using ideal gas law. So PV equals nRT. So this will give you volume equals nRT divided by P. So do we have everything? We have moles. Okay, the moles just calculated. Temperature is 23 degrees. We need to convert to Kelvin. Okay, so that's temperature. Pressure, 716 torr. We need to convert to atmosphere. Okay, so first unit conversion, 716 torr. divided by 760 to give you 0.942 atmosphere. And the temperature, 23 degrees Celsius plus 273.15 Kelvin, give you 296 Kelvin. And now plug in all the data, number of moles just calculated, R constant, temperature, pressure, give you answer 213 liter. Sample problem 5.13. The alkali metals react with the halogens to form ionic metal halides. What mass of potassium chloride forms when 5.25 liter of chlorine gas at 0.95 atmosphere, 293 Kelvin reacts with 17 grams of potassium? First, let's write the reaction equation. The reactants are chlorine gas and potassium, and the product is potassium chloride. So here is the reaction: chlorine gas, potassium chloride. To balance the reaction, we need 2 here and 2 here. And you can see in the diagram, when chlorine gas inside react with potassium, it releases a lot of heat, and a white solid forms, and that's the potassium chloride. So what are the given conditions? We have volume, pressure, temperature of chlorine gas. So the chlorine gas, we have volume, temperature, pressure. Okay. We also have 17 grams of potassium. So the mass of potassium is also given. And the question is, what mass of potassium chloride? So what is the grams of potassium chloride, okay, will be formed? So apparently this is conversion between reactants and the product. And since we have both the reactants, chlorine and the potassium, so one of them will be a limiting reactant. And therefore we need to find the limiting reactant. To do that, we calculate how much product is formed by each of them and choose the smaller one. So let's use the chlorine first. Okay, look at the chlorine first. In the chlorine, we have volume, temperature, pressure. To use stoichiometry, we need to convert to number of moles first. All right, and then from number of moles, we can calculate moles of product. So ideal gas law, PV equals nRT. So N equals PV divided by RT. All right, so first we calculate the number of moles of chlorine using given pressure, volume, temperature. So that's the moles of chlorine. Okay, and then we calculate how much product is formed, and the ratio is 1:2. Okay, so we calculate using number of moles of chlorine, and 1 mole chlorine equivalent to 2 moles of potassium chloride, and that gives you 0.414 moles of potassium chloride. So that's from chlorine. Next, we are going to calculate product from potassium. So we have 17 grams. We also need to convert to moles, and then from moles potassium to moles of potassium chloride. So 17 grams of potassium divided by the molar mass. 1 mole potassium, 39.10 grams of potassium. So grams potassium cancel, give you moles of potassium. And then look at the stoichiometry, is 2 potassium, 2 potassium chloride. And so using this conversion factor, so moles potassium, give you grams, give you moles of potassium chloride. Okay, so this is moles of potassium chloride. So compare these two. This one is smaller, and that indicates chlorine is the limiting reactant. And so the product formed must be this one, 0.414 moles of potassium chloride. To calculate the mass, we need to multiply by the molar mass. So 1 mole potassium chloride, 74.55 gram potassium chloride. And the answer is 30.9 grams of potassium chloride. The gas laws we have discussed so far can be explained and derived from Kinetic-Molecular Theory. This theory is based on a few postulates. In postulate 1, it says gas particles are tiny with large space between them. The volume of each particle is so small compared to the total volume of the gas that it's assumed to be 0. So gas molecules are just dots. In postulate 2, it says gas particles are in constant, random, straight-line motion except when they collide with each other or with the container wall. So in a container, there are dots moving randomly, constantly randomly in all directions, and they collide with each other and they collide with wall. The pressure is due to this constant collision. In postulate 3, it says collisions are elastic, meaning the colliding particles exchange energy but do not lose any energy due to friction. The total kinetic energy is constant. Between collisions, the particles do not influence each other by attractive or repulsive force. So the molecules are just dots moving randomly in all directions. Constant moving collision causes the pressure, and there's no attraction force or repulsion force between these dots. From postulates 1 and 2, each gas particle colliding with the container walls exert a force. Countless collisions over the inner surface of container result in a pressure. The greater the number of particles, the more frequently they collide with the container, and so the greater the pressure. So the pressure is due to the constant collision between these particles and the wall. It depends on the number of particles, the frequency of the collision, how often they collide per second. It depends on how fast the molecules move. It turns out that in a collection of particles, the speed of these particles are not the same. Some move faster, some move slower. There's a distribution of the speed among these particles, which can be mathematically described by Maxwell equation. This diagram shows the relative number of particles with the speed. In this case, we use nitrogen as an example. At 273 Kelvin, some molecules move very slow, for example, only 10 meters per second, but the percentage is small. More molecules move at, let's say, 30 meters per second. Okay, the percentage increase. And the highest percentage of the molecules is right here with speed around 50 meters per second. Now, some molecules move even faster. For example, even 1,300 meters per second, but the percentage is also small. So the highest percent molecules move at the speed of 50 meters per second, and this is called the most probable speed. When temperature is increased to 1,273 Kelvin, the most probable speed increase to 1,000 meters per second. Now, some molecules even move at 2,000 meters per second, but the percentage is small. The most probable speed is 1,000. Increase temperature to 2,233 Kelvin, the most probable speed becomes about 1,500 meters per second. So the most probable speed increases with temperature. Now, we know that the speed is related to kinetic energy. So this tells us that the average kinetic energy is proportional to temperature times a constant. So it depends on temperature. At a given temperature, all gases have the same average kinetic energy. Let's see how kinetic-molecular theory explains Boyle's law. Here is a cylinder with a movable wall, and inside the cylinder there's a collection of molecules, just dots moving randomly in all directions. At equilibrium, the gas pressure equals the external pressure, and there's an average distance between the gas molecules and the wall. As external pressure increases at a constant temperature, the average distance between the molecules and the walls decrease. Okay? And so the sample volume decreases. Collision of the particles with the walls becomes more frequent over the shorter average distance, which causes gas pressure to increase until it again equals external pressure. So increase pressure, decrease volume. Pressure, volume are inversely proportional. When gas A is pushed to another container to mix with gas B, the total molecules in the container increase, and so is the total pressure. The number of collisions of particles of each gas, A or B, with the container wall are in proportional to the amount of each gas, which is responsible for the partial pressures, PA and PB. And this added together is the total pressure, which is the Dalton's law. Here shows another cylinder with movable wall at equilibrium. When temperature goes up, the average kinetic energy of the molecules also goes up, and this will increase the speed and increase the collision frequency between the molecules and the wall, which will increase pressure. And because pressure of the gas now is greater than the atmosphere pressure, so the wall goes up, increase the volume. And when volume increased, the average distance of the molecules between molecules and walls also increase, and this will reduce the pressure until the new pressure equals the atmosphere pressure, and that will stop. So under constant pressure, increase temperature, increase volume, and that's the Child's law. Here again shows a cylinder with a movable wall and a gas with pressure equal to the outside pressure, atmospheric pressure. When more gas molecules enter into the system, the average distance between the molecules and the wall becomes smaller, and this increases the collision frequency and increases the pressure. And because pressure of the gas becomes larger than the atmosphere pressure, it pushes the wall up, increase the volume. The increased volume increase average distance between the molecules and the walls, and this will reduce the pressure, and therefore the pressure becomes smaller until the pressure of the gas equal to the outside pressure. So the outside pressure, atmosphere pressure, is kept constant. The number of moles increase, the volume increase, and that's Avogadro's law. Volume is proportional to the number of moles. In previous slides, we showed that in a collection of molecules, the molecules move at different speeds. Some move faster, some move slower, and there's a distribution of the speed. The most probable speed is determined by temperature. And we showed that the average kinetic energy of a molecule is proportional to temperature times a constant. And at the same temperature, all molecules have the same kinetic energy. In physics, we learned that kinetic energy is half m times v squared. So if we have compared two molecules, one kinetic energy is half m v squared, 1, okay, average, so the average kinetic energy for 1. For 2, average kinetic energy m2v2 squared average. If they have same temperature, then they have same kinetic energy, so these two must be the same. Now if m1 is greater than m2, then v1 must be smaller than v2 because the products are the same. So at the same temperature, a heavier gas particle moves more slowly than a lighter one. This diagram shows the relative number of molecules versus molecular speed at a given temperature. Hydrogen is the lightest molecule among all these molecules, and the most probable speed is the highest. Helium is heavier, and the most probable speed is smaller. Oxygen is the heaviest, and the most probable speed is the smallest. So the lighter the molecule, the faster the molecule moves. Diffusion is the process by which a gas escapes through a small hole in its container into an evacuated space. We already know that a lighter gas moves more quickly and therefore has a higher rate of effusion than a heavier gas at the same temperature. Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. A lighter gas has a smaller molar mass. 1 divided by a small number gives you a high rate of effusion. Sample problem 5.14. A mixture of helium and methane is placed in an effusion apparatus. Calculate the ratio of the effusion rates of the two gases. According to the Graham's law of effusion, the rate of effusion is inversely proportional to the square root of the molar mass. So the rate of helium over the rate of methane is 1 over square root of molar mass of helium divided by 1 over the square root of molar mass of methane. This equals to the square root of the molar mass of methane divided by square root of the molar mass of helium. And this is just equal to the square root of the molar mass of methane divided by molar mass of helium. In other words, the rate is inversely proportional. So helium over methane, here methane over helium. The molar mass of methane is 16.04 and the molar mass of helium is 4. And the square root gives you 2.002. Okay, question B. If it takes 7.55 minutes for a given volume of methane to effuse from the apparatus, how long will it take for the same volume of helium to effuse? Because the rate ratio is 2, that means helium effuses almost twice as faster as methane. So if methane takes 7.55 minutes, then helium must take almost half of this time. More precisely, you should use 7.55 minutes divided by 2.002, and that gives you 3.77 minutes.